and things like that, thinking about the experiment in general and what we saw and what we expected to see. Can someone start us off by just sort of, let's identify the edges in the corners. What was the experiment about?
We were observing a laser that was projected across the room through two slits, and we found that when the one laser beam went through the two slits, it created a series of dots, like beams of light on the wall, even though there were just two slits. So we were trying to figure out why the two slits created multiple beams of light on the wall.
Okay, so this may be obvious. I get that it created multiple beams of light on the wall, but why does finding angle theta, why is that important?
Do we use the angle theta to find wavelength?
Well, we found that it was like the same angle on like the big one, or like the difference. I don't know how to describe it without pictures, but like the little triangle that like had the wavelength at the bottom was the same angle as the big one. And so if we found
Let's go to the document,
Yeah.
right? I think the one that Anna is talking about is on the packet. It's on my latex packet.
Could be this one?
Yeah, right? Yeah, right? Anna, can you find the page that you were looking at? What page were you referencing?
Oh, is it proposition 3? Similar triangle.
Or, Anna, were you specifically talking about figure 2? What were you specifically talking about?
Does anyone else have the one that he handed out separately?
Yeah, I have that one.
I like that one.
I was just, like, on this it shows like the 3 thetas, and you can see that like on this one, like we determined that this is like the wavelength, and so if we can find that, like the thetas, then we can use it to find the wavelength.
And we proved using this model that they are the same angle because they are perpendicular, like this line with the red dots is the same as the black line to the green dots. And the K inside was the difference between the two angles, so they were the same.
Yeah, right.
So then we knew that if both of them had a 90-degree angle, because they're both right triangles, and they shared an interior angle, then the thetas must be the same, which means that we could compare them and use them proportionally to find the wavelength.
And because we know the, this value, we know the wall value, which is equal to the bottom of the blue triangle, then that can help us retray and find that wavelength.
Should we talk about why line EF is one wavelength?
Ooh, do we have like the textbook thing that has it's in the,
I have the equations, I looked up the equations, so give me a second to read it, so where is it? Okay, sorry, 1 second, I wrote this down a while ago. Basically what it is that, so that bottom, what was it labeled in that?
Was it this one?
Yeah, sorry, I don't have to.
Mason, can you talk a little louder?
Yes, so line E to F is equivalent to the wavelength because line, for the label on the, I don't think they're labeled, but the line stemming up from each side of that triangle, I have them as R1 and R2. Yeah, they're R1 and R2. R2 minus line R1. That's what would, and then that is also equivalent to the line, what is it? It's E to F, sine theta, which is the angle.
The reason that it's the wavelength is because, as like the textbook packet showed, where there's like the squiggly lines, when the wavelengths, like when they come to a point where there's light, they have constructive interference at the point, so then it adds and it makes light. But when they're destructive, they're dark, and since we were looking at points of light, and we know that it's constructive interference, so it would be represented by the middle one up there. And that is showing that like it has to be, the S1 in this model has to be exactly one wavelength bigger than S2 so that they line up again.
Right, it has to like travel one wavelength more,
Yeah.
right, to reach the same point, which
So then-
creates constructive interference.
Yeah, so the difference is the wavelength.
Can we, that was, can we repeat that? I'm just gonna try and grab this image. And again, let's just think about, how we can do it. There's a certain, sometimes we're working on our formality in Harkness discussions a little bit, that we can say specifically, in the textbook, let's all look at figure 24.3, right? And there's a little bit of a formality there, right? And I have it up on the board, but let's try and use some of that language. So now we've got it here, and it can really concretely bring together one of these corner pieces. And I feel like it was just said a moment ago about constructive and destructive interference. And so, Liza, could you repeat a little bit of what you had just said? So Maya brought in the image, and then Liza, you did a great job of adding on and looking at the language that we use, right? So we're sort of at this one here, right?
Yeah.
So this is figure 24.3, the image in the middle. And so what did we say about one wavelength and whatnot?
So I said that the beam in this one is coming from S1 because of its location. It has to travel one wavelength further to reach the same spot on the wall. Yeah, Mr. Rawson's drawing it. And then because of that one wavelength, like the way it lines up with the other wavelength, that creates constructive interference, which is why we saw the gray spot.
Okay. Now, if I could just highlight that, and I think you guys know, but I would highlight that as a corner piece of this experiment, right? So maybe let's call it that, right? Can you guys maybe take a moment, write out, and maybe summarize in your own words that phrase about constructive interference, and S1 is traveling one wavelength further, so therefore they're in phase, and therefore you're getting a bright spot. Because that will frame our work going forward in very clearly understanding what's happening.